So let's start with, so during 1 hour or so, I will use this presentation to introduce, to make a big introduction of what we are going to do during these 3 days. But first of all, our work is indeed to what we call the modeling world. So we are working in this modeling world. And I guess for everybody it's clear, but just perhaps it's good to have an illustration. So for us, a model is a simplified representation of some aspect of the real world we are studying, right? And so we have this kind of picture, for example. So this is a model of the stars and the planets, right? And so a kind of model like that can be a mechanical model or logical model or mathematical models. And indeed, the Bayesian network is in between a logical model and mathematical model, right? And you can see that we already have nodes here, right? So this is not so far from the Bayesian network. And once we have this model, then we will be able to use it to try to answer a question, right? So it will be more easy than directly working on the direct real world. So when we have a model, so the question is, why are we building a model? So it can be for prediction. So in order to be able to answer to questions such as, what is the priority that a given customer will be interested by your product, right? Or what is the priority that a company will fail, right? So this is one purpose for a model, the prediction. Or it can also be for explanation. So you want to have a model in order to analyze this model and find what are the main drivers in order to optimize sales, for example. Or to compute what are the real effects of a drug. Right? So these are the two purposes, so either prediction or explanation. Right? And then we have also sources. What are we going to use in order to build the model? So are we going to use just the theory, right? So we have an idea of what we want to do and an idea of how the world is working, right? So we will build the model by using our expert knowledge. So either your expert knowledge or the expert knowledge of the entire group, right? Or we can also use data, right? So this is a second source of knowledge to build a network, a model, right? And given that now we have introduced, why we are going to define or design a model and what will be the source we will use in order to build this model, we can define a map, right? In 2 dimensions. So we have the first axis is the purpose, and the second one is the source. And given these 2 axes, then we have this map, and we can define 4 quadrants, right? And in this map, so again, we have the purpose. As I said, this is either for prediction or for explanation, right? So when I say prediction, it's also description. So you have, let's suppose you have data, and you want to find what are the relationship between the dimensions that describe the world you are modeling, right? And here it's when you are trying to introduce causal assumptions, and then you will try to explain, to really understand what happened, right? And here is the source, theory, and here data, right? And so once we have these 4 quadrants, we will focus on this one right now, Q2. So this one corresponds to, you are just interested in finding association, right? And you have data. So this is exactly where big data is right now, right? So this is really active quadrant. And this is where you will find, scoring, forecasting, classification, and so on. And the idea in this one is you have a data set, and you want just to use this data set in order to predict something. So it can be, the best example we have in mind is for Netflix, for example, when they are using data in order to predict what is the next movie you will probably like to see, they don't care about the model itself, right? They just want to have a high precision rate, right? So this is exactly what Harsha was saying. This is a black box in this case. And sometimes they are even using more than one model. It can be a neural network, it can be a SVM, it can be a mix of different kind of models. And they will use that in order to have a high precision rate. And they don't really care about why you are going to see this movie, right? They just to have a high precision rate. So this is this one, right? And another interesting quadrant is Q4, where in this case, we also want to have a high precision rate, but we also want to understand, right? It's not just predicting something, having some kind of oracle that will give us the answer, but we want to see why, right? Why are you going to see this movie, for example? And this is more, in the economics or social sciences field. So this is where you will find the structural equation models, for example. And then once you have this, you have causal assumption, and you will be able to use your model for optimization, for risk analysis, and so on. So it's not just prediction, but it's really explanation, understanding the world you are modeling. Okay? So we have these two different quadrants, and we will see that by using the Bayesian network framework, we can cover the entire x-axis, right? And this is kind of unique to use just one framework to cover all this, right? So because we'll see in a few minutes that we can use a Bayesian network for just finding association among data, among the variables, right? And as soon as we are introducing some kind of causal assumption, we'll be able to use that for, for explanation too, right? So we can go from association to causation. And not only for building the model, but then also for reasoning, right? We can use the engine in order to do probabilistic inference, so either observational inference or causal inference, okay? And we can also, by using the same framework, cover the entire y-axis, right? So we can start without any data. So just by using your expert knowledge, and this is exactly what we are going to do today, this morning, we will build networks without using any data, just creating nodes by hand, adding links, defining priority distribution. So we will be exactly in this part, right? So no data, and usually when you are building a Bayesian network by hand, you are building a causal Bayesian network because this is the way we are reasoning, right? So we will be in this right part, right? And tomorrow we will, so this is, for example, an example of supervised learning where we have a target node. We can have 20,000 variables, and we will focus, we'll try to find what are the variables we need in order to predict this target, right? And in this case, we will really focus on the precision rate, right? Not really the understanding of the relationship between these variables. And we can also have this kind of, it's just an illustration of in between, here we have theory. So this is a network you are building by hand. And these white nodes are what we call hyperparameters. So this is really Bayesian statistic in this case. So we are going to use data, but not for finding the structure, but just for updating the priority of the hyperparameters of our parametrical model, right? So this is really expert knowledge plus data points that we will use for updating the parameters. And this last one is really what we call an influence diagram. So it's a Bayesian network plus two kinds of nodes, decision nodes and utility nodes, right? So this is really for decision making. Okay. And usually in these kind of networks, you don't have data. Even if you can use data to try to find the structure, but well, this is usually without data. Okay? So this being said, so you can see that a Bayesian network will allow you to cover all this map, right? And now I want just to focus on BayesiaLab, because BayesiaLab is based on Bayesian networks, but as I said, since 14 years, we are working on adding features on features on features, and then we can really cover every part of this map. And I will start with this one. So you can obviously use BayesiaLab for creating a network by hand, as I said, by clicking and using your expert knowledge. So this is knowledge modeling. You can create influence diagrams, so add decision nodes and utility nodes, as I just described. You can do Bayesian updating. So even if a Bayesian network is a non-parametric model, you can sometimes use that as a parametric model, defining your equation and then having your hyperparameters that will really, yes, define or parameter, be the parameter of the equation you have defined in the nodes, and then use data to update these parameters. You can do what we call parameter learning, so having one structure and use data just to update the parameter of your network without changing the links, right? You can do unsupervised learning, so it's between Q2 and Q3 in this case, because you will use data and create the nodes for each column you will find in your data set and try to find the links between all the dimensions, right? And in this case, all the nodes will have the same weight. So there is no target node here. You really want to have a model that will show you all the relationship between the variables, right? Then you can do data clustering. So trying to find, let's suppose your rows are individuals, trying to find groups of individuals that share common characteristics, right? You can do variable clustering. In this case, we are clustering the columns, right? And then this is based on unsupervised learning. We'll see that tomorrow. And you can also define one target node and do supervised learning, right? And as I said, when you are using all these methods all together, you can define a probabilistic structural equation models. Okay? And given that you have all these models, then you can use BayesiaLab for total effect computation or direct effect estimation. You can use that for target optimization. So you can really, as you see, cover everything with only one tool. And it's not just because sometimes you can use an IBM tool that will offer you structural or SVM, neural network, all this stuff. But indeed, you will be able to cover some part of this map, but using different theoretical framework. Here, the strength is this is only one theoretical framework, and this is really powerful, right? So we can thank Judea Pearl for creating this framework, right? So let's start with one really basic example, an example we are using since years and years. This is a medical expert system, right? So this is only based on, we are on Q4, fourth quadrant. So we don't have data per se, we just have expert knowledge. So to tell the truth, the data is inside the mind of this doctor, right? And he's about to retire, and he said, well, before leaving, I want to create a Bayesian network that will represent my knowledge, right? And then he said, well, I need to create, or I will manage 8 dimensions in this little world. I need to have 3 dimensions for the diseases. So I need to have 1 dimension for bronchitis, another one for cancer, and the last one for tuberculosis, right? So he is interested in 3 diseases, right? And then in order to characterize these diseases, he needs patient characteristics. So he needs to know the age, to know if he's a smoker or not, and if he went to Asia recently. Okay? And last, we have symptoms, dyspnea, and X-ray, the result of X-ray. Okay? So we have these 8 dimensions in this small world. Okay? And then, so we are going to create 1 node in a Bayesian network per dimension, right? So we have 1 node for visit Asia, 1 node for age, 1 node for smoker. Then the red nodes represent the diseases, so we have tuberculosis, cancer, and bronchitis, and the 2 symptoms, X-ray and dyspnea. And we have this one, which is an artifact. It's a logical OR. So it's true when tuberculosis or cancer are true. So it's just because for this doctor, if you have tuberculosis or cancer, this is the exact same impact on X-ray and on dyspnea. So instead of having 4 links that will cross, we are just creating 1 node that will represent this new, or the fact that tuberculosis or cancer is true. Okay? So it's just a way to simplify, to have a kind of factorization of our graph. So we have 1 node per dimension, and we have links that represent, in this case, because this network has been built by using expert knowledge, these links are causal links, right? But we will see tomorrow when we will start using BayesiaLab for machine learning, it will not be causal anymore, right? In order to have a causal Bayesian network, you have to say that this is causal. So there is no way to have something automatic that will say, oh, this relation is a causal relation, right? So you will have always, as an expert, this is your job to say this is a causal network or not. Okay? But in this one, as this has been done by expert knowledge, these are causal links. And we have here, so if it's not causal, it just represents a direct probabilistic relation between the two dimensions, right? So in this case, we have a direct link between visitation and tuberculosis. We have another one between age smoker, age cancer, smoker bronchitis, and so on. So we can see that this is kind of easy to read, right? So we see that, well, given that you are smoking, there is an impact on cancer. Even if right now this is purely qualitative. We cannot see if it's increasing the risk or decreasing the risk. We can imagine, but right now we cannot see it, right? We can see that there is also a link from smoker to bronchitis to dyspnea, and so on. So you don't need to have a PhD in computer science or statistics to understand that. So and this is one of the key points of Bayesian networks, right? Because you can do a very complicated study and then go to the boardroom and present directly your Bayesian network to the CEO, and he will understand that, which is not the same thing as coming with, you know, coefficient of regression and saying, p-values, and you say, no, I don't want to see that, right? But here you can really understand the story that is behind. So this is not a black box, right? So you see really the relationship between your dimension. Okay? So this is the first part. So we have one node per dimension plus links between the nodes. That indicates direct probabilistic relationship. And then we have parameters that are associated to the nodes. And we have two types of parameters. So in this case, this is really causal. So a Bayesian network is a directed acyclic graph, so you cannot have any cycle. So you cannot have at the same time age smoker and smoker age. So you have to choose one. And in this case, as this is done by using expert knowledge, this doctor says, oh, age is a cause of smoking, right? Even if you have a data set, you will find this relation, but you will not be able to know if it's age smoker or smoker age. And to tell the truth, when you have such a triangle, you can set the orientation in all the directions. It will not change the model.
By causal, we have to set it.
Yeah. As this is causal one, now you know that age is a cause of smoker. But by machine learning, you will not be able to know, right? Even if, for inference, you will have the exact same result, except if you want to do causal inference.
You just call it
Yeah,
association.
absolutely. Okay. So if we focus on this node, age, so there is no incoming links here. So this is what we call a root node, right? So in this case, so each of these nodes, as I said, represent one dimension, and we have states. You know, to have variables, we need at least two states, right? And this one has three states. So we have one for young adult, another one for adult, and the last one for senior. So you can imagine that this is a continuous variable, and that we have discretized this variable. And we will always need to discretize the continuous variable. Okay? So this is one of the conditions. And then, so we have three states for this node. And the thing now, we need to define the probability distribution for this variable. And as we don't have any parents, we just need to define this marginal probability distribution. And this can be done by using the expert knowledge of this doctor. So you will say, oh, since 40 years, I think I've seen 25% of young adult, 40% of adult, and 35% of seniors, right? Or you can also use a team. So we have a tool for that, for brainstorming. where we are using the knowledge of 15, 20 guys, or even more if you want. And by using a web interface, we are trying to reduce the cognitive biases, and then you will have a priority distribution that will reflect the consensus among this group. Right? And the last way to do that is to use data. So if you have a data set describing the patient, then you can just, it's really highly frequentist in this case. We'll just count in this database. We found 2,551 young adults, 3,982 adult, and 3,500 seniors. We are just normalizing in order to compute what is the marginal priority distribution. Okay, so we have these three ways to learn this, to estimate this priority distribution.
Can I ask one question?
Yeah.
On discrete data, means if we take a continuous variable and make like 3 different buckets, how we know the boundary of each bucket? Means like is our experience or
yeah,
just,
it depends. So if you have a target variable, let's suppose in your case the quality of steel, for example, and you want to do supervised learning, you want to find what are the predictor of good quality. So you can, and if you have plenty of continuous variables, you can indicate to BayesiaLab, this is my target, and I want you to find what are the best thresholds. And we will find that, right? So we'll find the best threshold in order to explain this variable. If it's unsupervised learning, it's more, you cannot just focus on one target. So we will use the priority or the density function in order to estimate where we need to put thresholds. So we have lots of algorithms that will analyze that and define the thresholds for you. Or if you have some expert knowledge, you can also manually set, no, for me, I want a threshold for less than 10 and so on. So you have all these possibilities.
Means we use classification models to find the threshold automatically.
Yeah.
Then you
So but for the density, we just forecast, you just pick based on, forecast.
No, well, we can do that, but this is the worst solution.
Yeah.
Yeah, yeah. So because we don't want to have equal size buckets. We will see tomorrow why it's really the worst decision. So we really want to keep the shape of the density function. So if you have a normal distribution, let's suppose you are using equal frequencies, you will have something flat, and then you are losing the shape of the distribution. So we want to keep that shape. Okay. Then, when you have a node with incoming links, so what we call parents, we need to define a conditional priority distribution, right? And in this case, so we are focusing on cancer, so we have 2 parents, age and smoker, and then we need to define for all the combination of the states of these 2 parents what is the priority distribution of cancer, right? So for smoker, it's a binary variable with yes and no, and for age, we have 3 states. Young adult, adult, and senior. So we have 6 distributions to define. So we need to define what is the risk of having cancer given that you are a smoker and a young adult. Then this doctor says, oh, it's 1%. And then 99% for no. Right? So the sum is equal to 100 for each row. Right? Then the risk when you are a smoker and adult, it's 5%. And smoker senior, 15%. So we can see that the risk is increasing from 1% to 15% when you are smoking. Right? And the same thing then for non-smoker. So it's 0.1 for no and young adult, 1 for adult non-smoker, and 5 for non-smoker senior. So the risk is also increasing, but it's lower. Right? So one key point here is that given that you have this kind of, you need to define a priority distribution for all the combination of the states, there is one important point here that the size of this table is increasing exponentially. So you will not be able to have, or you can, but if you have 20 parents, 20 binary parents, you will have 2 to 20 distribution to estimate. So it will be tedious, right? And even if you have a data set, you will not have a data set big enough to estimate this usually, right? So this is the reason why, for example, we have created this TBRCA, and this is one trick in order to reduce the size, trying to find, new variables that will summarize interaction between 2 or 3 nodes, right? Because even if you think that your target is directly depending on 20 nodes, if you set these 20 parents, this means that each parent will have an impact that depends on all the states of the co-parents, which is usually not the case, right? Okay? So now you just have to imagine that for each node, we have either a marginal probability distribution or a conditional one, depending on the parents. So for visit Asia and age, just 2 marginal distribution, and all the other ones have a conditional one. And this one is a deterministic relation. So the other one are with probabilities, and this one will be just if tuberculosis is true or cancer is true, then it's true with 100%. So we will have 100, 0, 0, 100, but nothing with 1, 99. Right? And then given that we have nodes, links, and probability distribution associated to each node, then this is a representation of what we call the joint probability distribution. So this is something I will use during these 3 days. So a joint probability distribution, it's a hypercube. Is it clear for you? Yeah? So it's a hypercube, in this case, made of 9 dimensions. And in this hypercube, so we have 1 dimension per variable. And then we have cells in this hypercube. And in each cell, we have a probability. The probability of being there with this data equal true, smoker, young adult, tuberculosis, no cancer, and so on, right? So we have lots of cells there, and we have probability inside each cell. And when you make the sum of all the probabilities that are inside the cell, it's just 1 or 100, if you want. Okay, so we have this hypercube. And when you know this, when you have this hypercube, you are the king of this world. You can compute everything, right? And the only problem is that the size of this hypercube increases exponentially too, right? So even with a toy problem like this one, it's impossible to have, or not impossible, but it's really tedious now to have a perfect representation of this joint. And then a Bayesian network is indeed a compact representation of this hypercube. So it's like a zip version of the joint. So we are compressing this hypercube, and we are trying not to lose too much information, right? And in this case, as this is based on expert knowledge, we are indeed not losing any information, right? Because if we want to have a theoretical representation of this hypercube, we need to have links everywhere. So everything should be connected. And then we will have a link from visit Asia to age, right? But we know that this is not worthwhile to represent this relation because there is no relationship between these 2 dimensions. So we can save this in the representation of the joint. And this is really what we are doing. This is exactly the same principle as zipping a file, right? So we have a compact representation of this joint. And once we have that, as I said, we are the king of this little world. And we can use this network as an oracle, if you will, and as what we call a probabilistic expert system. Okay? And then, the first thing we will be able to do is to compute marginal probabilities. So let's suppose we have people here waiting, and then somebody is knocking at the door of this doctor, right? And by using this expert system, now, the doctor will say, oh, even before the guy opens the door, right? The probability that the guy who will enter is a smoker is 46%. The risk of cancer is 4%, and the probability that he has dyspnea is 42%. So this is the prior knowledge that results from this representation, right? So just by knocking at the door of this doctor. And then the guy opened the door, and he says, well, I'm a smoker, right? So now we can indicate in this network, oh, we do not have any more uncertainty on smoker. Now we know for sure that he is a smoker. So we will set 100% on smoker equal yes. And now in this hypercube, we can focus on this subset of particles that are compatible with this evidence, right? And we will set smoker equal 100%. This will have a direct impact on cancer, right? And so indeed there are two paths in order to update that. There is this one, the direct one, smoker cancer, and this one, because we will, given that we know that he is a smoker, we will also update age, and this will have an impact on cancer too. So we have these two paths for updating cancer, and then the priority is 5.38, right? But this is also, the information is propagated to bronchitis and then to dyspnea. And then the priority of dyspnea is 54%.
How would you use both paths to calculate the age of cancer?
What do you mean?
So in other words, you go from smoker to age and then age cancer. How is that different than going from age to cancer?
So here there is a small cube in this case, right? So if you set smoker equal to 100%, you have a direct impact on cancer, right? And you also know that age has an impact. So you remember the table we had here? So we know that smoker and young adult and so on, we had the risk. But you also know that there is a link on these two. So it's not just reading the table. You have to take into account the joint priority of age and smoker. So what is the priority of being young and a smoker?
And that affects the distribution.
Absolutely. So it will not be the same result as just if you don't have this link, for example.
What is that age variable? Is that real age or how long it has been smoking?
No, age is really the age. Yeah. Are you young? So there is no, in this very simple example, you don't know if you are a big smoker or not. Okay? So we have, so setting 100% here, updating cancer via these two paths, and also updating TB or CA, dyspnea, and bronchitis, and X-ray, indeed. But not tuberculosis and visitation. We'll see that later. Okay? So this is what we can call simulation because we set evidence on a root node, right? And one thing that is really cool with the Bayesian network is there is no input or output nodes, right? If you have a model like that, you can set evidence everywhere. So you are not, it's not like when you use a neural network or regression where you are really doing something toward one node, one target. You cannot say, you will be able to use your regression model to compute what is the value of your output or dependent variable, but then you will not be able to say, what if this dependent variable is equal to 5, what will be the result on the independent variable, right? So in this case here, we can have all the variable can be input variable or output variable, right? So I'm setting evidence on smoker equal yes, because this is the same individual. And now it says, oh, I have dyspnea, right? I have some difficulties to breathe, right? So given that he's a smoker plus he has dyspnea, we can update cancer again. And now the risk is not 5% anymore, but 8%. Right? And this information has been also propagated to tuberculosis, visitation. So it has been propagated everywhere, even if the links are in the other direction. Right? So in this case, it's not causal reasoning, it's more observational reasoning. Okay. And then let's suppose we want to compute what is the effect of smoking on cancer. Right? So we want to do now causal analysis. So a naive approach will just consist in comparing smoker equal no with smoker equal yes, right? And see that when I'm focusing on people who are not smoking, I have a priority of 2.8 for cancer, and for smoker equal yes, a priority of 5.3, right? So we can just conclude that, well, the impact or the causal effect is 2.6, right? So this will be the naive approach for that. But if you remember the network, setting smoker to yes, I have a direct impact on cancer, but I'm also changing the priority distribution of age, right? So because we know that given, no, we did not see the table for smoking, but the priority is if you are young, you are most likely to be a smoker than when you are a senior guy, right? So if you set smoker equal yes, as you can see, we are reducing the expected value of age. And then we are focusing on people that are younger, right? And when we are setting smoker equal no, then the age is higher, 57 here, the expected value. So we are not comparing, so we are comparing smoker equal yes or no, but the population is not the same. Here we have a population with 57 years old, the average, and here 40. So by setting smoker equal yes, we are increasing the risk of cancer, but as we are also reducing the expected value of age, we are decreasing the probability of cancer. Because younger people are less likely to have cancer, right? So we have what we call a confounder here. So we have to be careful with that. So we cannot just do this kind of inference for computing causal effect. This is really observational inference in this case. We are really, it's exactly as doing a kind of selection in a database here. We are selecting non-smoker and selecting smoker, but it's observational data, so we have this bias here, right? So we cannot compare these two populations. So if we want to do causal inference in this case, we need to come back in the framework of control experiment, for example, and then to say, I don't want to have this probability distribution to change. So I want to compare smoker and non-smoker, but with the exact same population, or at least with the exact same expected age, right? And then you will see this in a few hours that we just have to make a right click on this and say, I don't want this probability distribution to change. I want to fix this probability distribution. And then we will be able to compare smoker equal no with smoker equal yes, with a population with an expected age of equal to 49, right? And then, as you can see, the probability of cancer is 2.2 and 7.5. So the risk is not, the effect is not 2.1, but it's 5.3.
That's the same as removing that connection, right?
Yeah, but if you remove the connection, either you are using the do operator that we have, or if you remove it manually, then you are destroying your graph. Okay. So this was the first example. So we were in Q4, right? So now we go in Q2. So we have data, and we want to find relation between the variables that are in the data sets, right? So we want, but just association, right? And for this, we are going to use the stock market, so the S&P 500. So we have historical data there, and we want to find, the relationship between the companies. And we have 6 years of historical data. It's day return by company. And this is just a subset of the variable we have. So it's really 6 years, even if we are not going to use here the temporal dimension. So we just have this 1,500 data points. And we want to see if there is a link between A and ADP, for example, or AES, given this data. Right?
Is that change or it's absolute value?
It's a change. So here is just a snapshot. If you use Excel, for example, to see the relationship between the stocks, and it's just a subset of this because we have 500 companies, right? And as you can see, it will be kind of tedious to do that this way. And then here is what you can have after a few seconds by using BayesiaLab. So you are just loading this data, and BayesiaLab will see that we have 500 columns. We have data for each day, and we will create one node per stock. Right? And in this screenshot, it's more, or it's still by the network, but you can see that the visualization is kind of different. We have different size, right? So a node, now the size of a node is directly proportional to the strength of this node in the joint priority distribution. So the bigger a node is, it means that if you have some insight on this node, then you will reduce the uncertainty around the other one. Okay? And we also have the thickness of the links that is also directly proportional to the strength of the link. Right? So we have two additional dimensions in this case. And this is particularly useful when you have a big network. So you can use this tool even with 20,000 nodes, and you will very quickly see what is important. Because without that, you will have a big network with 20,000 nodes connected, and you will not know where you have to start your analysis, because everything has the same size. And so in this case, you can see very quickly that we have 5 or 6 big companies there. So we can really zoom in just to see what that is, right?
The basic question that you asked in the beginning, though, relating to the data was?
So here we want to see what are the connections between the companies. So if one company is increasing by 5%, what is the probability that another one will increase or decrease by X%, right? So without any expert knowledge, just looking at this historical data, right? So it's not it will not be a causal model, right? It's not because I see that there is a link between Dell and Apple, then I will be able to do something. If I do something in order to increase the stock value of Dell, I'm not sure it will have an impact on Apple. But looking at the history, you can see that they are moving together. Okay?
What's the minimum data? What do you think?
The size, you mean? It's a big question. We will cover that tomorrow, indeed. But just very quickly, it really depends on the uncertainty that is attached to your world. For example, with industrial data, you don't need a lot of data usually, because this is almost deterministic, right? You know, if you set temperature to 100 degrees, then your water will boil, right? So it will not be deterministic because you have some problem with your sensor or captor and things like that, but otherwise it's quite deterministic. But with data coming from surveys, human beings answering to questions, you need more data just to be able to reduce. And for survey data, it's usually 500 will be the...
Yeah, we, during product development, if I want to use it, what are the minimum number of experiments in the mill have to do?
Of experiment, you mean?
Yeah, means new product, basically.
As I said, it's
That's
not...
what we are struggling.
Yeah. It's not easy to... Yes, if you just have 10 samples, it will not be okay.
Depending on depending on complexity of the system.
Is there a measure?
Yeah.
Is there a measure?
But the problem is, if you don't have enough data, you will not be able to find any link, because we will see tomorrow morning that the algorithm we are using to find if we need to add a link is based on information theory, and there is a trade-off.
But that's also when results are first realized something.
Yeah.
That's when you
Can you merge Q2 analysis and Q4 analysis to come to a better understanding of what's happening for a model?
You mean mixing expert knowledge plus... Yeah.
Like I could see some conclusions being made with big data to just inform a node in a larger theory.
Yeah, you can do that.
Yeah, so
even if it will not be direct, there is no tool that will allow you to do that, but you can use the knowledge you have you have discovered by the data mining to build your expert knowledge.
Yeah.
And sometimes you can also do the opposite, so using your expert knowledge just on a subset and saying, wow, I don't want any connection between these two universes, because that does not make sense. So you can forbid relation. You can also say, I want to have a connection from this one to this one, even if it's not really in data. So there are lots of ways to merge expert knowledge. You can even start. Sorry. You can even start with a structure. So with this kind of network, you will not build your own network with 500 nodes. But for a smaller one, you can start with your structure and say, this is my prior, and I want to mix this prior with data.
Are the links here
Let me
measure independence or dependence between the nodes?
Yeah, so when you, for example, we in this one, as you can see, we have a kind of, we are discovering clusters of companies, right? So here we are in the energy field. And when you have a link between these two, this means that this one is Progress Energy Incorporation, linked to Scana. This means that when you know that this company increase or decrease, then this one also increase or decrease. But as I said, again, and this is really important, this is not a causal link, right? So even if I am able to change something there, I do not have any guarantee that it will impact this one. Perhaps it will, but I have no guarantee.
So you could use historical data to define condition problems.
Yeah. So here, in this case, when we are learning that, so at the very beginning, when you load the data, all these companies are disconnected, right? Then you click.
So it's observational.
Yeah. Then we are analyzing the data, finding the links, and estimating the conditional probability distribution. And then, given this, we have a model of the joint, which is, in this case, a really big hypercube, because it's a hypercube with 500 dimensions. And we can see that, oh, indeed, this link is stronger than this one, for example. So we can analyze that and yes, give you some feedback.
So the fact that they are linked is because, so when you fed this data in, there was probably something that said industry.
Nope,
You know,
nothing, no expert knowledge at all. And this is the reason why we are using this model, because it's not really useful for investing, but it's useful for showing that this is something that works. You know, for example, when I worked some years ago for glass companies, you know, so they have production of glass for windshield and things like that, and you just arrive there and say, okay, here is our historical data. You click, you learn, you find connection between it, and usually people are saying, oh yes, I knew that. Yeah, but you are working in this area since 20 years. I'm just arriving, so, and I can tell you that indeed there is a relation. And then there are other relations that you are not aware of. And say, oh yes, it's true. What is that? So it's just to say that here, no expert knowledge, just raw data.
Just the data.
And as you are kind of expert of this area, you can see that, oh yes, I knew that, but I can see that it's purely automatic. So I can do the same thing with the Chinese market. And you are probably not an expert in this market. I'm not. and we'll find connection between these companies too. Okay. And when I say that it's not useful, indeed, yeah, the guys from from Wall Street just say, well, yeah, we can still use that, because if you want to make a combo for investment, we can select, you know, companies that are far in the graph, just to reduce the risk of the investment.
Yeah, like portfolio management.
Absolutely. Okay.
Well, but also, historically, you know that the standard principle, you know that maybe in the future it's not going to really change. Like in my world, crash environment doesn't change that much, so it's kind of very valuable too.
Yeah. But except in this case, as this is financial data, you know that we are just observing things, but there is so many hidden variables behind this that it's really, this is just a summary. Yes, we have sensors there, but yeah, we cannot use that for causal analysis.
Yeah, like example is transgender line, but when Senate, when Congress passed the bill, the share price increased. When Senate rejected it, down. It's political aspects and other.
Yeah, but it can also be something for. We were yesterday speaking with Kristen Array, which worked for the CIA on all these things, and she's analyzing, you know, using this market relation in order to find if there is something happening. So, for example, with the recent, or with Ukraine, you know, with the Russians there, just by analyzing the market, she said, well, there is no threat, because if there were a threat, a very big threat, that we would be able to see an increase in all the army industry in Russia, and nothing is moving. So this is just, they are just playing right now. So it was kind of interesting to learn that.
So this would be a snapshot at the end of the day, maybe closing share price, something like that. But
Yeah.
Can you make it, is there even the computational power to like grab this real time? Because this isn't temporally sensitive. I don't know
Nope.
which happened first.
Nope.
You find
To
a
make
median
this
in
change, yeah, so do I tend to see this one grow and then this one grows, or this one grows and then this one grows?
Right now, yes, this is just a snapshot at the end of the day. So
End of the
yeah,
day.
yeah.
Because I'm just trying to,
But nothing says you couldn't take every node on here and make it like 4 nodes representing 4 days in a row.
Yeah, you can do you can have a dynamic Bayesian network.
yeah.
And similar like retirement funds, like how it affects, like we can make sure that this investment decision won't depend on each other, so that one will be safe.
Yeah.
Okay. So this one, for example, if we focus here, we have all the CPG industry. So P&G, Quaenox, Heinz. So this is really the ecosystem of Procter & Gamble here. And you have the electronic part here in this one. And then we have, the stores, hotels, and
Oh, that was beyond related to staples.
what that?
That was beyond. That's right side. It's connected to staples.
Oh, that might be on.
Which one? I don't. This one.
Those two.
So I don't know why. Is there a link or?
Yeah, Walgreens series, yes. Yeah, but and it's
Any of you have this company there? No.
Sorry.
You don't have. Nobody is working in one of these companies.
Yeah, I'm trying to think.
Well, it's interesting that Target is so much more significant than Walmart, but Walmart is so much bigger. You would think I had because it's financial.
Mhm. But so this data was pulled just on the end of the day with one
Yeah.
closing price. So this implies that Target moved that day, whether up or down, we don't know. But the price moved, but Walmart's didn't. quite
No.
move that
It really means that. Let's take this example. This one. Oops. I don't know if you know this one, for example. Franklin Resource. This is the strongest node, and almost nobody knows this company. And this is just a company, an investment company. So indeed, this is almost the S&P 500 index. And so when you know the evolution of this company, then you are reducing the uncertainty on American Express, Intel, Pfizer, and so on. So this is really not causal. This is really one sensor of the market here. Right? And the size of the node is directly proportional to the number of connections you have and the thickness of the link. Because if you have lots of connection but very thin one, it will not be important.
And there are no direction, right? There is no direction.
No.
So did you have to, when you took this data from the Excel file, did you have to validate it or troubleshoot it to get it to this point, or does it just?
So you will see that we are loading data, learning. So if you just want to do that quick and dirt, you can just learn and you have the result. Then if you really want to exploit that, you can do cross-validation and things like that to be really sure that you have the best model. Okay?
Means it's not just at, are we like putting like industry segment or like that to make it more?
Then you can define, if you have some expert knowledge, you can define classes, for example. You can say, okay, I will define my own segment, and then you can say, I don't want any relationship between these segments, or I don't want to have relation between this segment and this other one, or inside this segment. So you have lots of degrees of freedom for that. But in this case, the idea is really to create the segment automatically, right?
This is,
Yeah.
You know, shoe industry should not raise the fence, something like that, that you know that it doesn't make sense.
Yeah.
So you brought up Congress earlier, and the bill, I guess it makes sense because we're in DC, but I mean, you could probably do this too with legislation and specific committees. So a really active committee like Senate Finance, you'd see a lot of connections to a lot of different pieces of bills, or maybe sectors versus maybe like a science committee that's not as active, or
Perhaps, yeah.
resources committee which isn't as active. So it's just a way of showing you sort of where the action is happening.
Yeah, if
and
you have
what
really,
direction it's
if you are in
affecting.
influencing or not.
Yeah.
So, and the question is always, because we can, I was talking about brainstorming a few minutes ago, so we can also build the network by using a group of experts, so this is something we are doing a lot. And then at the end of the session, we can do data mining on the probabilities that have been done or given by the expert and find the relationship between these experts. And then we have this kind of mapping with the size depending on the, so in each node then is a guy in the room. And sometimes you have one guy in the middle, big node, and then you say, wow, is he the influencer or is he just following everybody? And you just don't know. Well, when you are in the session, you can infer, but just looking at the network, you don't know if he's really the one who is influencing all the other one, or if it's just, yes, listening. And
That would make sense with an investment node. That explanation that you just gave.
Well, with brainstorming, the thing is you can, when you are in the session, you can really see, or it's not so easy, but well, you can, depending on the behavior of this guy, you can see if he's really following or giving advice and everybody is listening to this guy. For the market, it's, I think it's much more difficult, or unless you have some expert knowledge too, but you know.
It's more like the anchoring point of it. Means like when we go for negotiation, if I propose something, then everything build on it. Or whether he's thinking here or he's anchoring with my point in place.
Absolutely. Except that, yeah, in our brainstorming solution, we have something, it's a web-based solution just to prevent these anchoring biases. So, because otherwise, before, some years ago, we were just saying, well, what do you think about this priority? And everybody was, oh, for me, it's 90%. And it was over, because once you said 90%, everybody will go around 90. So now we have something like, it's like a Delphi method. So nobody is talking, everybody is using his computer with sliders to give his advice. So now we are reducing that. But still, once you have given your advice, you can talk and justify why you gave this. You gave these priorities, and then you can influence the other one. So, yeah. And this is also what we are looking for, because we just don't want, so we want people to share knowledge. So.
You also want a diversity of knowledge, too.
Yeah. And then, so once we have this kind of network, we can analyze the strengths of the connection and create segments. Right? So this is variable clustering. So we can automatically, based on this network with 500 nodes, we can create one with 25 nodes. And then we will create meta nodes that are, yes, clusters of stock here, in this case.
Just, I don't mean to beg the question, but the strength of the node has to do with the compatibility of the movement, or the...
They are not necessarily compatible. Indeed, they are linked. Right? So in this example, everything is positively correlated. But you can have something negatively correlated, or you can have something nonlinear. We don't have any hypothesis behind. Okay. So this is a way to have clusters. And then I will use this last example to show how we can use Bayesian networks for building what we call the probabilistic structural equation models. And this is an example we will use not tomorrow, but the day after tomorrow. And this is a French example with perfume. And so it's based on a survey. So this is the reason why we need more data, because we know that as you are answering to a question, even in the exact same condition, you will probably not give the same answer if I ask you that now and the same question tomorrow, right? So we have in this data set 1,321 respondents and 12 fragrances, right? And in this survey, we have some variables that describe the product. Is this perfume sweet? Is it flowery, feminine, and so on? We have some question about the imagery. So when you are wearing the perfume, are you sexy, modern, in love, and things like that, right? And then we have one node for the intensity of the perfume. So is it strong, or too weak, or just about right? So this is really something non-linear. And we have, at the end of the day, our target, which is the purchase intent. Right? So once you have tried that, are you going to purchase this product or not? Right? And we want to use all this data in order to find what are the drivers. So this is not just for prediction here, this is really for explanation. We want to be able to understand this universe in order to find what are the drivers in order to increase the purchase intent. So we don't want to see, given this evidence, what is the priority that she will purchase, but we want to know what we should change in our product in order to increase the purchase intent. Okay? And here is our probabilistic structural equation model. So you can see that we have blocks. So the first step of a probabilistic structural equation modeling is to find the relationship between what we call the manifest variable. And the manifest variables are all these variables here on the periphery of the graph. So these are really the questions that are in the survey, right? So the first step consists in using unsupervised learning to find the connection between the questions. Then, so this is the same thing as what we did with the S&P 500, finding the connection between the nodes. Then we are analyzing this graph and creating clusters of variables, so clusters of questions in this case. And based on that, we can say, oh, these four variables are strongly connected, right? And we are just speculating that this is representing a concept. So there is a hidden cause behind that explains the relationship between these four variables. And we have another one here, freshness, another one for testing, another one for adequacy, and so on. So automatically we will be able to find these concepts. Right? And so this is the same thing as in the S&P 500, the big nodes we had for creating the segment. Right? But then, given that we have these new factors, we will create nodes. So we will create a new node that will summarize this small hypercube. So we know that these four nodes are strongly connected. We are speculating that there is a hidden cause, and then we will create this node. So it's a latent variable. So it's not in your survey, but it will be at the end of the day. Right? So we will create new dimensions. So if you have 50 nodes, at the end of the study, you will have a network with 60 or 65 nodes. So we will create, in this case, 15 new nodes. Right? And each node that we will create, like factor 1, 2, 3, 4, 5 here, will be a summary of the nodes that are in this box. Right? And then we will find the links between these new latent variables and connect, or try to find connection between the target node, the purchase intent, and these new concept nodes. Right? So it's a kind of hierarchical Bayesian network. So we have two layers. The first layer corresponds to the answer that we can read directly in the survey, and then the first layer are the concept we found. And the link is, the target is only linked with layer number 1, not with layer number 0. And in this case, you know, it's like changing the zoom in an image. So you have lots of pixels, and in our case, we are just saying, okay, no, we don't care about all these points. Here we can see that this is the face of the guy. Here are the legs, here are the arms, and so on, right? So we are changing the zoom in order to create these ones. And by doing that, we are losing information indeed, because we are building summaries, right? So as I said, with respect to Q2 we want to have a high precision rate. Q4, we know that we still want to have a good precision rate, but we prefer to understand things, right? So by doing that, we are losing precision rate. So let's suppose we want just to have very high precision rate for our purchase intent. The best thing to do will be to just do a supervised learning and directly connecting purchase intent to all the questions, right? And then we'll have a good precision rate. But then, when we will use this network, it will not work, because we know that these women The same question 1 or 2 or 3 days later will not answer the same thing. And then we will have a very good model for this survey, but it's not useful for trying to find what are the drivers, right? So this is, the conclusion here is saying, it's okay, we can lose some information, but then we will build strong concepts. And then these concepts are much stable. And based on the relationship with these concepts, then we will be able to, yes, to have to use this survey to optimize a product. Right?
So I've been recently studying structural equation modeling, and I'm aware that there's PLS SEM and covariance-based SEM. Is your probabilistic SEM one of those?
No, it's really, well, we are calling, this is, we call this probabilistic structural equation model just because this is the same, this is absolutely not the same approach, but this is
So it's
kind of,
different from both?
yeah, this is a competing approach for the answering to the same question. So for example, this is a key point of our relationship with P&G. You know, we do have a worldwide strategic partnership with Procter & Gamble. They are using this for improving their 300 products, 300 brands every day all over the world, right? And before this partnership, they were using structural equation models. But then for one, so let's suppose you are in charge of Mr. Clean. As you can see, I'm very close to my customers. and so the PR guy, just so he knows he has his survey data and so on, so he knows his product. And then in order to build a structural equation model, this is really, you need a PhD in statistics for that, right? It's not easy. So they had to send the data to these guys in Cincinnati, and these guys they were not aware of Mr. Clean, so they had to struggle. And in order to have the answer, it was 2 months, right? And now with that, the PR can directly use BayesiaLab for this, and it's not 2 months, it's 2 days, and with much more powerful answer and things like that. So this is the reason why they are really, yes, they spread that very quickly across the world.
And so are they doing market segmentation, basically?
No, it's really trying to find its segmentation across the dimension, across the variables.
Here. What I mean, like when we do survey, when we survey like US, Asia, and Europe, if you treat as each segment as one market, then the taste will change, means the relations will change.
Yeah, so in this case it will be, yes, you will do something per zone, if you want.
It's local.
Yeah.
The data. Means if I do survey in Asia, I cannot apply here because
sure. And even in Asia, you know, if you are analyzing data or building a model for I was in Singapore 3 months ago for P&G, also for whitening products, so for the skin, and the behavior of Chinese and the behavior of Japanese is absolutely not comparable. So you are still in Asia, but you cannot have the same model for them. So you need to focus to have different kind of model.
Yeah, I read one story that India develops this sticks, baking sticks, that are smoke. I heard that I think the Thailand, Malaysia, they like some fish smell taste. Fish smell. They researched and finally they developed in India like no one likes, except one state. No one like fish smell.
Yeah.
But they like fish smell. I mean, that's why they can market segmentation.
Yeah. But in this case, yes, this will be done more. So we will see that here, indeed, we are just focusing in France, so which will be different from Germany, for example. But to go, it's almost the same thing, but we have 12 products, so we can also have, it will not be the same network for each product. So we will have the same structure, but different parameters, one per product, which is almost the same thing. We can also build a network for a worldwide network, and then estimate the priority for each country. Right.
It's by enhancement adequacy, they can meet most of the market demands. Because both are connected.
I'm sorry?
It's connecting like enhancement and adequacy. Focusing on those two, they can like 60% of they can satisfy 60% of customers.
I'm not sure I got it.
Because the purchase intent
is 70%.
17% influenced by enhancement. And 43% by adequacy. Enhancement and adequacy, those are related.
Yeah.
That's if you combine, that's a strong relation.
Yeah. And at the end of the day, this is just for communication purpose when you have the graph, because I set the percentages here, so the way you can say, oh, indeed, if I increase evoke joy by 1 point, I know that there is a 57% of impact on factor 1, and then 17 on persons intent, so you can already do some computation. But at the end of the day, you will not use that like that, because BayesiaLab will directly compute for you what is the optimal points. And then it will tell you, well, you need to do this, and this, and this. And if you do that, you can expect to have X% of increase. So this is really for, yeah, for communication, saying, well, what is important, but for decision making, you can directly use the tool. Yeah. Okay. And then, so once you have this network, you can use it for what-if scenarios. So what if, by using that, you are increasing by 0.8 feminine, 0.8 furry, so you will have the impact on purchase intent, and you will have the impact on all the other dimensions too, right? Then, even if, as I said, we have to discretize everything, and here we have not continuous variable, but numerical variables, so we have to discretize them too. But then we can go back to the continuous world and create, by using interpolation with soft evidence, if you want, we can generate different points across the variation domain of each variable. And for example, in this case, the blue curve, this one, corresponds to feminine, right? So we know that if we decrease by 6 points feminine, then we will decrease by 1.5 points the purchase intent. And if we go there, if we increase it by 2 points, we will increase by 0.6 the purchase intent. So we can see that we have, so this is one per driver here, right? And we can see that almost everything is linear, except this one, right? And this is the intensity of the perfume. So if the perfume is not strong enough, you are just losing your money, right? You can say, I will not purchase this product because it does not last, right? If it's too strong, you can have headache, right? So you will say, oh, no, I will not use it either. So there is a just about right level. And this is the same thing with sugar, with salt, with all the sensorial stuff. There is always, this is what we call the just about right variables. And they are always nonlinear. And these are the worst to optimize, right? Because let's suppose this is sugar. You know that people, these guys are, they thought that there is not enough sugar. So in order to increase the satisfaction of this guy, you will increase the level of sugar. But then those, they already thought you had too much sugar, so they will be even more unsatisfied. And people that were just about right, they would start to say, oh, no, now it's too much. So it's not easy to optimize, right? But the key point here is a Bayesian network is a non-parametric model. So we don't have any hypothesis of linearity, any hypothesis of anything. So we just throw the data there, and then we'll be able to find this kind of relation, right? Then this is what we call an opportunity plot. So this kind of these are the tools that you will be able to use in 2 days or even tomorrow. So we still have the value on the x-axis. This is the value of the current driver that we are analyzing, and the y-axis is what we call the mutual information. So this is a kind of correlation of this variable with the target, right? And then very quickly we can see that feminine is the dimension that has the strongest connection with the target node. And we can also read that the satisfaction level is 7.3 or 4 on a scale of the maximum value should be 9 or 10 here, right? So we can see, so if you have one driver here, really important with a very poor satisfaction, so this is something you have to work on, right? It will be easy to increase that in order to increase the purchase intent. And as I said, it's on a set of products here. So we have 12 different products. So you will be able to hover over one point here and see the satisfaction level of all the competing products. So it can be competing product, it can be countries, it can be states in the US. So you can have analysis based on the country, the entire country, and then have one point for each state of the US. Right? And the thing is, we are going to use this information to generate realistic optimization scenarios. So if I want to optimize product number, let's suppose I want to optimize product number 2, I will try to say, well, I know that one product number 8, has a satisfaction level of 7 for freshness. So I will try to reach this level, because I know that this is something doable. Okay, so we will use this competing information to generate realistic scenarios. We will not do, well, what if I'm able to have 100% of the women satisfied with my new action? So we know that this is not doable. But then, by analyzing the other product, we can see where are the best ones, right? And then generate this kind of trees, for example. So this is a tree that describes various optimization policies. And then by analyzing this tree, we can directly see what are the most important drivers. Okay, so we will cover that in 2 days. So just a few words about Bayesian belief networks here. So a few questions you should be able to answer at the end of the training. So what is it for? First one. So this is really a decision support tool, right? So this can be for, you can use that for analysis, so either data analysis or even expert knowledge analysis. So you will see that in a few minutes when you will start building Bayesian networks, it's easy to build a Bayesian network, but it's not easy to use it. So you need tool in order to analyze your knowledge in it. Right? You can use that for simulation purposes. You can use that for diagnosis or a combination of both. You can use Bayesian network for optimization, for risk management. So these are the main applications. Then the second question is, how can you build a Bayesian network? There are three ways to do that. So the first one is using expert knowledge, right? As we saw with the doctor. So it can be either using expert knowledge of one guy or a team, right? So as I told you, in Singapore 3 months ago, we had a team of 20 experts from P&G covering all Asia, right? And then we are interacting with them, building the network, right? Second way is to convert something else. So we can have some, for example, a reliability block diagram, and then we will be able to analyze this model and convert this model in a Bayesian network. So this is something that we can do. The only problem, usually, you still have to estimate the probabilities, because these are not probabilistic models, right? Or not, do not have all the parameters. And the last one is by consists in using machine learning algorithm, right? So we can use machine learning for unsupervised learning, so no target. Supervised learning, you have one specific node. Data clustering, variable clustering, and exactly the case with the perfume, the probabilistic total equation models. The application domains, at least for Bayesian. We are working a lot with market research companies. So they are using that for customer segmentation, collaborative filtering, scoring, drivers analysis. So this is example with the perfume, marketing mix modeling, market share simulation. We also have lots of customers in the industry field. They are using that for diagnosis, product optimization, operational safety, anomaly detection, sensor fusion. And some in the strategy, so HR, so human capital development policies, for example, performance management, political studies, project management. So all these, so and you can see with these groups that everybody is doing something different. So you can really use Bayesian networks everywhere. And then what is Bayesian networks? I already talked about the hypercube, right? So this is a joint priority distribution. We are using a directed acyclic graph for representing, to have a compact representation of this joint priority distribution. And this directed acyclic graph is made of nodes for representing the variables, and links to represent direct probabilistic relationship, and we have conditional or marginal probability distributions that are associated to the nodes. Right? And once we have this representation of the joint, we have a very powerful expert system, so a probabilistic expert system that we will be able to use it for reasoning under uncertainty, either for causal reasoning or for observational reasoning. And when we are reasoning with a Bayesian network, we can use hard evidence and soft evidence. So hard evidence is when you set 100% on one state. Soft evidence is when you still have uncertainty. So you are just changing the probability distribution of your nodes, right? And you can use that for simulation, diagnosis, and combination of both, right? So no input nodes, no output nodes. Everything can be input or output. Okay? Then this is one interesting question. Why this is called a Bayesian network? So I struggled during years and years, at least in France, because, you know, with the frequentist and the Bayesianist, and they don't want to hear about Bayesian stuff. So, and I was just saying, well, this is a Bayesian network, but this is not really Bayesian statistics, even if we can do Bayesian statistics, but this is probably more frequentist than Bayesianist at the end of the day. And Julia called that Bayesian network just because when he created this framework, the only way to build a Bayesian network was creating it by hand, right? So if you are building a network, it will be probably slightly different from yours, even if you are modeling the same world, right? So this is subjective. So this was the first thing. The second one, it's because it's based on the Bayes theorem, right? Everything, this is a generalization of the Bayes theorem. And the last point is because we can do observational inference and causal inference. So these are the three reasons why Julia called this Bayesian network. And the scientific fields that are implied in the research of Bayesian networks, the most active one is computer science. Then we have cognitive sciences, statistics, now that we are using Bayesian network for data mining, so statistics is there too. And as we are doing causal reasoning, philosophy is there too. Okay. And just to conclude this introduction, a few words about Bayesia. So this is a company we have created in 2001. So we are two co-founders. We don't have any statistician in the team, so everybody is computer scientist, right? And so we are 7 now in France. We have this Bayesia here in USA with Stefan. The same thing in Singapore. I already talked about the relationship we have with P&G, so with this worldwide strategic partnership. And we have some resellers and partners. And this strategic partnership is really something important, not only because there is money there, but also because this was a very good way to improve the software, because there are, I don't know how many users, probably more than 300 users in P&G, and so we have developed, I don't know how many features just for them. So not just for them, because they were asking for them, but then it was inside BayesiaLab, so it's public now. But it was a very good way to improve the software and then to be able to communicate with statisticians, because as we were computer scientists, it was not always easy to understand statisticians. So now we have p-values and all this stuff. Even if we are not using these p-values for building the network, this is an output of learning algorithm. Okay? As the name of the company indicates, we are 100% focused on Bayesian networks. And here is a set of customers. So just to illustrate that we are working in different kind of areas, so ranging from UCLA, so for indicating that we are working with universities, Unilever, the same ecosystem as Procter & Gamble. We are almost working with all the market research companies like TNS, Ipsos, Millward Brown, all over the world. Communication company, consultant, Booz Allen Hamilton, L'Oreal, Metro, hotel group, bank, automotive, transportation, electronics, NASA, pharmaceutical companies, glass companies, and so on. So at the end of the day, as this is really for decision making, each company can use that, indeed, right? So there is not one specific field. And as I said, we are computer scientists, so we are designing softwares. And so you have BayesiaLab right now. I already spoke about Biki, so this is our web solution for brainstorming sessions. We have one tool for computing market shares for new products, so this is a Bayesian market simulator. And we have a Bayesian engine, which this is an API that allows you to use our inference algorithm inside your own IT system, right? So you can design your Bayesian network with BayesiaLab, and then if you want to, I don't know, to compute some score, but on a daily basis or second basis, you can, instead of using BayesiaLab, you can use the API for designing your own application, okay? And so we are doing also some services, training, consulting, and some custom software development.